Hello, this is the second in a series of videos talking about the possible force and acceleration problems that exist when we're trying to find net forces and accelerations on objects. In this case, we have multiple objects being pushed with a single force. Well, at least right now it is a single force. I could possibly put friction on there, but then it would be more like the multiple objects with multiple forces, slightly different because in this case, well, we'll talk about the forces involved here in just a moment. So I may add friction in just as kind of an addendum to the questions I've already asked here. But in this case, we have two objects, both being pushed by one applied force. I wonder what's the acceleration, and then what are the net forces on each individual object, and then kind of some forces going back and forth between the objects. And so we'll get to those in a little bit. But following kind of our general guidelines, once again, there's kind of the overall, kind of 6 steps that we should be thinking about as we're working through these problems. So we'll take those kind of as appropriate working through this problem. So first thing is to draw a free body diagram. So in both of these, we do have a force of gravity going down, and M1 is 10 kilograms. M2 is 10 kilograms, M1 is 8.6. So since M2 is a little bigger, right, the force of gravity force should be a little larger. These both have a normal force going up. And so maybe, let's see, this is M2, so I'll just call that Fn2 for mass 2. This is mass 1. Kind of running out of room here, but F normal 2. Right, so we have F normal 1, got to keep track of my numbers. So there's normal force on the first object, normal force on the second object. And then what we have is we actually have an applied force on M1, and it's kind of at the top, but I don't know, I'm just going to call that F, that's the applied force. And then we also have a couple of other forces in the middle. M1 is pushing on M2, but M2 is also pushing back. And so my diagram's getting kind of small here. Let me just zoom in for a moment so I can maybe, oops, sorry, the wrong direction. You can kind of see what's going on with those. There we go. Now it's kind of focused. All right, M1 is definitely pushing on M2. So this person is pushing on M1, and M1 in turn is pushing on M2. But then M2 also has to push back. So M2 is also pushing back on M1. Now, one of the things with these diagrams, once you get them, is trying to figure out which things are the same and which things are not necessarily the same. And some students try to make just the leap that if this is a single number, whatever it happens to be, and in this case it's 46 newtons, then this one has to be 46 newtons too. And that is not true, because we have this person pushing on M1, and then M1 is pushing on M2. There's different objects pushing on each other, and if there's different objects, they may be completely different forces. And in fact, in a little while, I think we'll figure out that those are. On the other hand, these two forces do have to be equal and opposite, right? And I don't know if we want to call this maybe Fm1. I think my diagram's a little small here. And this one could be Fm2. Right? The force that M1 is pushing with and the force that M2 is pushing back with, those have to be equal. Because we have one surface and two objects, that is what creates what we call a force pair, when we have two objects pushing on each other. Here we have two different objects pushing on other objects, right? This is pushing, the person is pushing on M1 and M1 is pushing on M2. That is not a force pair. It is a force pair when we have the same two objects pushing on each other. M1 is pushing on M2 and then M2 is pushing back. Those two forces do have to be equal because they do create one of these, once again, force pair. And we can call them a force pair. In your explanations of things, if you want to say these two forces are equal and opposite because they create a force pair, from the terminology we've set up in class, that is a perfectly acceptable explanation as long as you're using it for the right forces anyhow. So I'm just going to kind of zoom out. Hopefully you can put those in your own diagram, maybe draw the diagram a little bigger because I'm going to lose a little bit of that kind of detail as I zoom back out so you can see the writing here. All right, now in terms of the numbers and what we need to do, so the first thing is drawing the diagram. Of course, maybe I should kind of let you see that here for a minute again. So we talk about part 2, which ones may or may not cancel. Actually, these two are going to cancel, the force of gravity and the normal force on box 2, because once again, those are two forces. Maybe we should zoom back in again. We've just thought of a very important kind of point we need to make here about these forces that cancel and which ones don't. These two forces are going to cancel because they're on the same object. Force of gravity is pulling on M2. It's pulling down. The normal force is pushing up on M2. And that's an equal and opposite force. We know that because objects do not normally accelerate up and down. And if the acceleration is 0, then the net force up and down has to be 0. Now, if these boxes did start bouncing or something, then one of these may be larger than the other. But we're assuming that these boxes are on a nice horizontal surface, and the only way they might accelerate is horizontally or sideways. If there's no vertical acceleration up or down, the net force up and down is 0, which means these two have to be equal because they are on the same object. Right? And the same kind of logical thinking goes for M1. Force of gravity on M1, the normal force on M1, they cancel. But going back to this force pair again, this force and this force are equal and opposite. The force that M1 pushes on M2 with and the force that M2 pushes back with are equal and opposite, but they do not cancel, because they are on different objects. M1 is pushing on M2, M2 is pushing on M1. So even though those forces are equal and opposite, they are on different objects. They do not cancel. They're going to be part of our equations we'll use here in a few moments. The F normal and FG, they do cancel because they are on the same thing. Force of gravity pulling down here, normal force pushing up there, are both on M2. They will cancel. But M1 is pushing on M2, M2 is pushing on M1. Equal and opposite sizes and magnitudes, but they're on different objects, so those we cannot get rid of. Right? I don't know of any other way of explaining that. If that didn't really work, you can always dial up YouTube or just start Googling why don't force pairs cancel, or why don't action and reaction forces cancel, because that's what most people tend to call them when they work through these problems. And then you can get 3 or 4 or 5 or 500 different explanations, and maybe one of those may make a little more sense. But yeah, action reaction forces or force pair forces never cancel because they are on different objects. All right, but the normal forces in gravity do, so we can leave those forces of gravity do, so we can leave those out of our equations. If I'm looking for the F net on M1, then I actually have two forces. Right? I have the force that I'm pushing with, and we can just call that F. And going back to our diagram, I'm going to let you look at that. Hopefully you've diagrammed it out, and so I'd have to kind of keep flipping back and forth here. That is pushing to the right. But we have the one that we labeled force M2, which is also pushing back on M1. So we have the force we're pushing with to the right, but M2 is pushing backwards. If I'm looking for the net force equation on M2, the only force that we have on that is the one that we just labeled F M1, right? The force that M1 is pushing forward. So, what do we know about these things? Well, we do know that this F on M1 and the force in M2, they are equal and opposite. So see, they didn't cancel because they are here in our equations, but these two things are the same number, right? So we can actually interchange them. So the net force on M1 is going to be this force that we're pushing with minus the net force on M2. Now, it seems like we have a lot of things that we don't know, but let's put in what we do know. Net force is directly proportional to the acceleration, right? In other words, if we go back to our acceleration formula, acceleration is net force over mass. So to solve that for F net, we have F net equals mass times acceleration. So on M1, our M1 mass is 8.6. So if this is 8.6 times whatever our acceleration value is, that's going to equal the force we were pushing with, which is 46.1 newtons, right? And that is going to equal the mass, minus, there's a minus sign there. Got to read my own writing. The net force at M2 is 10.1 kilograms times the acceleration. So this is the net force on M1, this is net force on M2. Now the thing is, both of these accelerations are going to be the same. Right? If we're pushing on a set of boxes in contact with each other, they're going to act like a single box. Right? The first box, let me just kind of go back up to the drawing again. Said I wasn't going to flip back and forth a little, but I think we need to point and talk a little bit. This box cannot accelerate more than that one because its inertia will want to kind of keep it where it is unless this box is pushing it. This thing's not going to take off and just fly out all by itself, because then M1 would no longer be pushing on it, and that would stop happening. On the other hand, M1 cannot accelerate faster than M2 because it can't like run over it and go faster and accelerate faster than M2 because M2 is kind of in the way. So if that's kind of how you want to think about it mentally, that's not the worst thing in the world. There are more technically correct ways of looking at it, but that works, right? So these accelerations have to be the same. So what we can do is actually put those things together, right? So if we bring this over, we get that 18.6, oh, excuse me, 18.7. Man, I cannot do math today. I apologize. 18.7 times the acceleration is going to equal 46.1 newtons. So then our acceleration is 46.1 divided by 18.7. And we have 2.5, the 2 sig figs, meters per second squared. And so that will be the acceleration of both of the boxes. Now it says, what is, so that's the answer to question A, right? It's kind of all of this put together. We need to figure out to do that. For question B, it's the question is, what is the net force on just M1? Well, we can go back up to this equation, right? And just plug in the numbers and find out. So we're going to take the equation right here, right? And plug in the numbers. So the net force on M1 equals the 46.1 newtons minus the force on M2, which is 10.1 times 2.5. And we get oh, helps if I hit the right numbers in the right order, I guess. Let's try this again. And okay, and then we have to subtract. I'm sorry, my calculator all of a sudden is just not doing what I want it to do. So let's try this one more time. There we go. I got 19.7, give or take. There you go. And then part C says, what is the F det on M2? Which is going to equal. Well, the only force on M2, right, was that F1 pushing the other direction, right, which was this part of that force, right, because that was, it says right here, F net on M2. 10.1 times that. So if we just multiply those two things, and I have 25, because I actually went back and used the 2.47. This was 2.47 before I rounded it off. I went back and used that number, and it's 25 newtons, give or take. So those are the net forces. And then we go up to D. It says, what is the magnitude of the force of N1 pushing on M2? And what is the force of M2 pushing on M1? Right, that is this 25 newtons. There's 25 newtons of forces pushing back and forth between those two objects. And once again, they're going to be equal and opposite to each other, but they don't cancel because they are on different objects. So, once again, the question is, well, let's see here. And that's question F. The applied force is 46.1 newtons. So if this one's 46.1, give or take, right? Why isn't this one being pushed with 46.1? This one's only being pushed with that 25 newtons. How is that possible? Well, that's because this force is pushing on here, and part of that force, I don't want to say is used by, but part of that force accelerates this object. Right? It's only part of the force that is transferred onto the second object. And how much of it? Well, how much of it came through our math and our equations, and we've got 25 newtons. Once again, give or take, with the sig figs and things, depending upon how you round this, you might get a slightly different answer. Normally, when we go to an answer like this and we round it off and keep 2 sig figs, we might still want to keep, like it was 2.47, that number to go through and work the rest of these, maybe rather than as 2.5. And then we'll get answers that are a little bit more accurate for each one of these, and then we can round them off to sig figs individually. But in any case, this is the process of working through these again, coming up with some equations off of the drawing, reasoning your way through how these forces combine together, putting in the numbers that you know, and then doing some algebra and finding the other forces that you don't know yet. In any case, this is the sort of treatment that you would get if we have multiple objects being pushed by or pulled with one force. Once again, and that happens, right? These things will have exactly the same acceleration, just because it's the contact forces between them that are causing those accelerations to be identical, and they should be able to work through the problems. Thanks for watching.